Okay, so let's talk a little bit about hypothesis testing. So, as usual, kind of in nonlinear models, everything is more complicated than in linear models. Yeah, naturally. Yeah, that's the bad news. The good news is that, of course, in any software package, everything is already implemented for many, many years. So, in Stata, everything means pressing a button. Yeah? So, for you, there's not so much work to do then. However, it's important to understand what is actually going on in the background. So for instance, in nonlinear models, you would consider a null hypothesis of this form. So we have like some function of the true parameter of the parameter. Some function of the parameter is equal to 0. Okay, so now y equal to 0? Well, I mean, we say this kind of stuff. It's actually a very general way of writing constraints. Yeah. So, for instance, if you wanted to say that a certain, for instance, you say, for instance, the first component of theta is 0. Yeah? So then you would simply define R such that you isolate the first component of theta minus 0 here. So kind of that would give you exactly that hypothesis that the first component is 0. Yeah, or you just kind of, as you want to test the hypothesis that the first component is twice as large as the second. Yeah, well, then you would kind of write R such that, you know, this is a matrix. So that kind of takes the first minus the second. And okay, what did I say? The first is twice as large as the second. So then this would be minus 2, I guess, or something like that. But anyway, you can do whatever type of hypothesis you want. Everything is captured with this framework. Okay, so how do we do this test? Well, there's a couple of ideas, and a popular test is the wall test, and that's a very easy test. And this kind of estimation is required for the unrestricted model. Yeah, so it means that we kind of estimate only the original MLE. Yeah, so for instance, let's say we have 10 variables. The restricted model says, okay, the last 2 of those are 0. Yeah? For the wall test, you would simply compute the MLE, including all of the variables, all 10 variables. And then what you would do is that you would kind of calculate this statistic here and evaluate it at the MLE. So what is this thing actually doing? Well, I mean, we're looking at the distance of this function here to 0, yeah, where the distance is measured as kind of like the quadratic form with some sort of variance estimate in the inside. Now, okay, so you would ask yourself, okay, so here we have the variance of the MLE itself. So what is this other stuff here doing? Yeah, so that is coming from the so-called delta method. The delta method is also something that is hugely important. What is the delta method doing? Well, I mean, it helps you to find the asymptotic distribution of functions of your estimators. Yeah, so for instance, here we have the original MLE. We know that it converges in probability to normal distribution with mean 0 and some variance B. Then if we take, instead of the original parameters, a function of these parameters, the delta method tells us that this still converges to a normal distribution. The mean is not changed here, but this is only because it was 0. So in general, it may change. And the variance can now be computed by multiplying the derivative of this function from the left and from the right. Okay, so therefore going back here, this thing is now actually an estimate of the variance of R of theta hat. Yeah, so kind of the function that gives you the restrictions of your hypothesis. Now, what can be shown is that this statistic converges in distribution to a chi-square distribution with q degrees of freedom, where q should be the number of, is it the restrictions? It's the whatever is left, I think. Yeah. Okay. So under the null, this converges to a chi-square distribution, and under the alternative, W hat just explodes. Yeah? So therefore, this test should also have good power whenever the null is actually false. Now, the wall test is super easy to compute, and it's a very simple idea. A big disadvantage is that it's not invariant to reformulations. Yeah? So, for instance, look at this thing here, which basically says that theta1 times theta2 is equal to 1, which simply means that theta1, for instance, is the same as 1 over theta2. You can write the same thing like this. It's the same information. But however, if you use the wall test, the same type of restriction will give you a different test result, or potentially different test result. The statistic will change. And this is, of course, not good, because in principle, you can mess around with your restrictions and get a different test result, even though you can basically cheat. That's the short story. And that's you don't want people to get the opportunity to cheat. So another test procedure, now we have to estimate only the restricted model. So kind of in the example where we had 10 variables, the last 2 are 0, kind of under our hypothesis, we have to now only estimate the model with like these 8 variables that are left. So what does the Lagrange multiplier test do? Well, it basically says that intuitively, if the null hypothesis is actually true, then the score at the restricted MLE should be close to 0. And again, what we are doing is that we are sort of testing, we're sort of looking at the distance of the score evaluated at the restricted MLE to 0. Same idea. Again, we have this quadratic form. The score comes from the left, the score comes from the right. And in the middle, we have some sort of an estimate of the variance. And this estimate of the variance turns out to be simply just the variance of the restricted MLE. So here it turns out that because of score unbiasedness and the information equality, applying the delta method here is not really needed. So kind of here you simply get the variance of the restricted MLE. Okay, so and the same thing applies here, kind of with respect to the asymptotic distribution. If the null hypothesis is true, then this thing will converge in distribution to a chi-square distribution. And if the null hypothesis is false, this LM statistic will explode. And therefore, we should assume, or we should expect good power properties whenever the null is actually violated. The final test that I would like to point out is the likelihood ratio test. So what we do here is that we take the likelihood itself and we compare it in the restricted and in the unrestricted model. So kind of when we base it on 8 parameters or on 10. Now, if the null is really true, then the likelihood, which should be similar, because if these 2 variables that we excluded are really not relevant, then it should not make a big difference for the likelihood. Okay, so what is the likelihood ratio test then doing? Well, as the name suggests, we are looking at the ratio of the likelihood under the restricted model over the likelihood in the unrestricted model. Okay, and yeah, so again, kind of if those 2 models are very similar, that really means that this likelihood ratio will be close to 1. And well, if that is the case, then we should actually prefer the restricted model. So the smaller model that gives the same information is always to be preferred. Now, the test statistic itself is based on the log of this likelihood ratio. And we have to invoke this times -2 here. Now, where this is coming from, well, this is actually coming from a Taylor expansion. So if you look at the proof of this thing, then, well, this is coming just from the Taylor expansion. So there's not such a big deal here. We don't look at the proof in this course, but the proofs are easy to find. Now, this likelihood ratio test has one disadvantage because it's, we see here that we need to evaluate the likelihood ratio. Both we need the restricted MLE and we need the unrestricted MLE. Yeah. Okay. So you have to do two estimations. Okay. However, what is a big advantage is that it's invariant to reformulations, which means you cannot cheat. And moreover, it's also computationally attractive. So because you really use all the information that is captured in the likelihood. Whereas WALT and LM test, they only use certain features. For instance, they only use the first derivative and the second derivative. For the likelihood ratio test, you use the full likelihood and implicitly, therefore, all derivative, if you want so. Okay, so these are three popular tests. And now we talk about different types of nonlinear models, and in particular about censoring and truncation. Yeah, so kind of sometimes we have a model that is actually linear, but the response variable is some sort of restricted, and therefore we need to treat this model as if it was a nonlinear model. For instance, what is happening when we censor data? Well, that typically happens. So there's a difference between censoring and truncation, which means that the covariates, the x variables, are observed as they should be. However, the outcome variable is constrained. Yeah, so for instance, let's say you have an income study and you only report for the very rich people that they have an income more than 100K. Yeah? So that means like your y variable, the income, is top coded. Yeah? So at some point you have like a flat response. Yeah? But the x variables for these people, you can still observe like without any problem. Truncation happens when, for instance, so under truncation, you don't have anything. You don't have y, you don't have x. That's basically the difference. So if instead of kind of keeping those rich people in your sample, but you just top code y, you were just to exclude them from the sample, you just drop them, then you would have truncation rather than censoring. Now, another example where truncation typically happens, yeah, so let's say you look at insurance data and you look at your outcome variable is sort of losses, yeah, how much would the insurance have to pay? And let's say kind of for any damage to your car that is less than 500, you would have to pay it yourself anyway. And now someone scratches you scratch your car, are you going to report that to the insurance? Well, I mean, if the damage is less than 500, it's not worth the effort, right? So any losses less than your deductible, 500 euro, you would never report, and this would lead to truncated data. Okay, so now a little bit like just this in formulas. So y star is again latent. That's for instance true income. However, we don't observe y star itself, but only part of it. So for instance, if the observed y is left truncated, when we only observe y as the true y star when it's bigger than some number L. So that would be the example with the deductible. So kind of if the loss is bigger than 500 euro, we will actually observe the reported losses, because otherwise no one will report. Same story happens kind of, you have right truncation or truncation from above, like for U, which is like upper. It's the same thing. Now you would assume that this latent variable has a continuous CDF with some continuous density F star. And you can actually obtain the density of the truncated variable y, because this y is simply the same as y star, conditional on y star being bigger than L. Otherwise, you don't see anything. So kind of like the density of y is 0 whenever y star is, this should be y star actually, sorry, I think this I'm gonna check. 1 One second. I have to look in my text file now at the side. So I put here star, and then it should be right. Yeah, so kind of it's going to be 0 whenever y star is less than L, and whenever it's bigger than L, it's basically this. Yeah, so it's the true density, but here you have to divide by some scaling factor because everything, all the mass that is kind of to the left of L is going to move to the right. Yeah, so that's kind of sort of the intuition here. And well, I mean, the next equation, again, that's something that you can look at just carefully. What we're showing here is that f of y is truly a density because it's measurable. You don't need to care about what that means. It's just measurable. That comes from measure theory, complicated stuff. A density has to be non-negative. That's also true. Yeah? And moreover, it integrates to 1. So that's kind of what is shown here. So this truly is a density. Now, instead of truncation, we can look at censoring. That's very similar. However, you kind of, here before, we kind of didn't observe anything when, for instance, y star was less or equal to L. When we have censoring, we observe the lower censoring. We observe the lower bound. Or when it's right censored or censored from above, we observe the upper bound. And yeah, let's try to derive the density of the observed y under left censoring. So kind of that's what we're gonna do. And again, so what is happening here? So why is this turning into a nonlinear model? Well, because kind of at L, everything that is left to the L. So think of it as there's a normal distribution and we get censoring at 0. So all this other half is going to have a point mass at 0 now. Kind of because when the distribution is -10, and we will only observe 0 because we only observe y and not y star. So what do we get? Here we look at the CDF, the big F, if you want so. Yeah. The CDF is 0 for any z that is less than L. At L itself, it jumps. That's the point mass. That's because we push the whole distribution up to L into this one point. And from L onwards, well, we just get this point mass plus whatever kind of the distribution of the original y star gives us. Yeah? Okay. So here now how to write the density of y? Well, we define this indicator here. The indicator just tells us whether y is bigger or than L or not. And yeah, so then you can simply write it like this. That's pretty much how you would write the density. And of course, once you have the density, you can write down the likelihood. Once you have the likelihood, you can maximize stuff. And that's basically it. Okay, quick break. And we continue with Pobit and Hackett and all this kind of stuff in a second.